Hello and welcome back to Let's Code Physics. We have had some success simulating the travel of electrons in a wire under the influence of an electric field. Last time we were able to create a couple of wires and see the electrons traveling in each of them. In order for us to create a circuit, though, we need to connect those wires. So that's going to be our goal for today, is to see how we can do that with our VPython code, is to have the two wires be connected physically and have the electrons go from one wire to the other. Before we can do that, though, we first need to look at specifying what direction the wires are. Last time we just specified whether they were vertical or horizontal. And so basically that just gave us an idea of the direction of the orientation of the wire, but that didn't really tell us what direction we expected the electrons to go in each of those wires. And so here what we're doing is we're making a distinction between up and down. So that shouldn't be the word differentiate, that should be the word distinguish. There we go. So what we're doing up here is we're saying if the direction is down, then we're going to flip the axis of the wire. The axis is just a vector that we're assigning to the wire. So if it's vertical, it's going to be in the Y direction. If it is horizontal, then it's going to be in the X direction. And basically by checking for down and left and then making this a negative, we're going to have the axis point in the other direction. That's not going to change how the wire appears. It's just going to change how we set up the electric field in each of those wires. So that's the first change we've made. Then down in the move electrons routine, in order to change the direction of the electric field appropriately, we take the magnitude of the electric field from here. So we are specifying the electric field magnitude for the circuit. And then we're multiplying by the wire's axis. So before, the electric field was its own vector because we just had two horizontal wires in the same direction. But this time we are multiplying that electric field with just the magnitude times the axis. So this tells it whether to point left, right, up, or down. And then the next big thing we need to do, if we're going to connect these wires, we need to have electrons be able to go from one wire to another. You remember before we had to put in this wall collision down here where if the electron reaches the edge of the wire, it needs to bounce off of it. Well, if we're going to have electrons move from one wire to another, we needed to actually be able to pass through the boundary of the wire it's in, but only where the two wires intersect. So what we're doing in order to accomplish that is we are checking over every wire in the list that is not the wire that the electron is currently in. So this num is the electron's current wire, and we're basically checking over all of those and checking for whether the electron is also contained in that other wire. So this if statement here is basically evaluating whether the electron could also be considered to be in the second wire, or in the other wire that we're considering. It could be the second, third, fourth, fifth, or 10th wire. And if it is, then we're assigning it to that new wire. Now what that means is that while the electron is in the overlap, it's going to alternate between being considered in the first wire and then in the second wire and then back to the first wire and then back to the second wire. It's not actually changing the location of the electron, it's just changing which wire we're labeling it with, which basically amounts to a 50% probability of which wire it's in. It's not a perfect solution to the problem, but it does get as we'll see in a second, it does get the electrons to transmit from one wire to the next. So it's working for us right now. Another thing I've done is to change our average position calculation into an average speed calculation because I am tired of messing up my rise over run slope calculations, and so we're just going to have it calculate the speed for us. The way we're going to do that, though, is we're going to record the average speed. This is really the average speed along the wire, because we don't know whether we want the X component or the Y component. So what we're doing is we're using the dot product. So the dot product picks out of two vectors the product of the overlap between the two vectors. So if two vectors are parallel, it gives you a very large product. If two vectors are perpendicular, it gives you zero dot product. So we're taking the dot product between the electron's velocity and the direction of the wire, the axis of that wire. So actually that is technically the average velocity, because that could be negative if our electron got bounced back the other way. I've got this print statement in here in case we want to check how many electrons are in each wire, but we should be able to see from the animations that they'll move from one wire to the next just fine. So we'll leave that out for now unless we need it, but I don't think we will. Okay, so what I've done is I've set up two wires. These are different than the wires that we had before. The first one is going to the right, and you notice that the -5 in the Y location. So this is going to be kind of the bottom middle of the screen. It's going to be downward. It's going to have a width of 10, or a length in the X direction of 10, and it's going to be pointing to the right, meaning the electric field is going to be driving the electrons rightward. Our second wire, wire number 1, because VPython starts counting at 0, so this is wire number 0, this is wire number 1. In fact, I'll even put in a note here. This is wire number 0. Number 0. It looks funny having a hash mark and a comment. This is going to be wire number 1. There we go. And so this one, on the other hand, is going to be vertically oriented. It's going to be going in the upward direction. And you see that it's moved to the right by 5, but it is centered vertically. That's going to give these two, as you'll see in a second in the visualization, that's going to give these two a little bit of a corner of overlap. Obviously, well, maybe not obviously, but hopefully the larger the overlap we have, the faster the electrons will spread from one wire to the next. And then we're going to set up our 30 electrons, and we're only going to set up electrons in wire number 0. So we're putting all of the electrons into wire number 0, and we're putting none of them in wire number 1. But what'll happen is, or what's supposed to happen, is that these electrons, when they're in wire 0, are going to get an electric field pointing to the right. When they go into wire number 1, they're going to get an electric field pointing up. And so once they get into wire 1, they should start moving up. So we should see our electrons go to the right and then up wire number 1. And we're creating these at the center of the of wire number 0, so they'll have a little bit of time to go from one wire to the next. The rest of the code remains unchanged. So let's run this and see if we get what we expected. Okay, and that happened faster than I intended. Let's go back for the slow motion replay. We can slow it down by turning down the rate here. So let's have that run about 100 times slower. So our electrons start out here in the center of wire 0, the center of the horizontal wire. Oh, I may need to increase the rate. As the electric field here pushes them to the right, they're going to go over this way. Actually, let's maximize this. There we go. That's better. So our electrons are under the influence of the electric field going this way. And like I mentioned, our two wires have a little cube of, or I guess it's a rectangular prism. They have a rectangular prism of overlap here. Now you notice there's two electrons in here. One of them bounced back off of the wall here, but there's a 50% chance that, like this one, they will pass through into wire 1. So once they've passed that barrier, like this one, they're considered to be in wire 1. If they go back into this region, there's a 50% chance that they'll end up going back into wire 0, but it's also possible for them to transmit through to wire 1. And basically, once they end up in wire 1, they have an electric field accelerating them upward. So they're no longer being accelerated to the right. They're being accelerated upward. And they're also subject to wire 1's wall conditions, to where they're going to bounce off of its walls now. And lo and behold, we get more electrons leaking over into wire number 1, because, like I said, these electrons are being accelerated to the right, and these electrons are being accelerated up. You saw it in the faster version that the electrons all end up piling up here in the corner. So it looks like we've got about half and half at this point. And once they make it significantly past this corner here, since they're under the influence of the electric field pointing upward, they're not as likely to go back this way. And so we end up with our electrons going from wire 0 over to wire 1. The neat thing about our graph now, ooh, that'll fit nicely in this corner, won't it? The neat thing about our graph now is that we are basically combining the speed along this wire with the speed along this wire, because we're taking the dot product for the electron velocity based on which wire they're in. And after their initial ramp up here, things get somewhat steady. I'd like that to be a little bit steadier, but that would require us to, I think, average over time as well as the number of electrons, and I need to work that into the code. And by now we've got all but looks like 2 of the electrons have transferred over to wire 1, which is a good thing to see. I think we can increase the rate a little bit. I was having to do a whole lot more talking than I anticipated there. So what'll be fun to see is if we can successfully change these things. So for example, what if we made wire number 0 point to the left? So that should make the electron, which they do. Now you notice I'm still getting a positive number for the speed. That's because the wire axis is pointing to the left and the electrons are traveling to the left, so that's a positive dot product. Now of course there's nowhere for them to go over here because I haven't moved this wire over yet. So the next thing I can do is take wire number 1 and let's move it over to the -5 location in the x direction. And lo and behold, our electrons, they go over to the left and they end up in wire number 1. Or they go from wire 0 to wire 1, just like we expected. They'll end up collecting up here. Very cool. Now I mentioned that, they've got to be in this little rectangular prism, so we could increase the size of that. Let's see, how much would we need to move wire 1 over in order to increase the overlap? Let's see, what's the width of my wires here that I'm creating? The width of my wires is 1 by a half. Let's make that a -0.5. Move it down by a half and move it to the right by a half. We should have a larger overlap between them. Okay, yeah, so now we've got as large of an overlap as possible between these two. And you notice that the electrons file in a little bit more quickly because they've got more region in which they can, let's see if I can get an action shot here, because they've got more of a region in which they can transfer from wire 0 to wire 1. Now of course it also means they've got more of a region to transfer from 1 back to 0, but I'd like to think that it works out in our favor. So there's our wonderful connected wires there. Of course, this is unphysical in the sense that we would need more wires going around here to make a complete circuit. That's what we will take a look at next time, is completing this loop so that we have a full circuit and have the electrons continue around and around the circuit. We'll do some testing of Ohm's law with that. And we'll see what we get. So thank you so much for watching. I will see you next time. Bye-bye.